Hi, I'm Bowen Heinrich, a student at Stellenbosch University doing my honors in operations research. The topic of my research assignment for the year was the minimum color cut problem. But Bowen, I hear you ask, what is the minimum color cut problem? Well, that's exactly what I'm here to tell you. To begin, let's consider a graph with nodes and edges. The minimum color cut problem specifically focuses on a graph with colored edges. The objective is to find a way to divide the nodes into two groups so that the number of colors between the groups is as small as possible. For example, if we divide the nodes like this, there are 4 colors going between the groups. But if we divide the nodes like this instead, there's only 1. What I actually considered was a more specific case of this, where 1, there are an even number of nodes in the graph, 2, we want to divide them into 2 equal groups, and 3, edges of each color form cliques. In other words, if a node is connected to 2 other nodes by a certain color, those 2 are also connected to each other by that color. The reason for these is because, despite this problem seeming quite abstract and theoretical, it actually has real-world implications for retailers. At distribution centers, products are placed on a picking line, around which workers walk, selecting products to be sent to each retail outlet. If they could find a way to split the picking line in half so that as few retail outlets need products from both sides as possible, the company could save time and money by having employees only walk half cycles of the picking line. Now, each node in a graph represents a product on the picking line, and each color represents a store for which products need to be picked. An edge of a certain color exists between 2 nodes if the associated products both need to be picked for that store. This is why each color forms a clique. Now you may be thinking that this problem doesn't seem too hard, but it's worth noting that, in the real world, these graphs are generally a lot bigger than this one, with more than 50 nodes and more than 1,200 colors. Since solving problems this big would be far too slow to be useful, I implemented MetaHeuristics to solve the problem instead. MetaHeuristics are OR techniques that use some form of randomness to find solutions that are good enough, in some sense, significantly faster. Many of these have been developed over the last few decades, such as genetic algorithms, variable neighborhood search, taboo search, and simulated annealing. I implemented a few of these to determine which would be the best for this particular problem, and found that one called variable neighborhood descent was